Hello and welcome to this repair video of the Yaesu CD-41 fast battery charger. Now I've done two repairs in the past. One was the repair of this Kenwood TMD700 where a transistor was faulty, and the other one was the Tentec Argonaut 5. That is actually not yet completed. I was hoping to do that last weekend, but I want to do it together with my dad, and since his retirement he's a very busy man, so I'm afraid that you have to wait 1 or 2 more weeks on that one, but we're going to complete that one. In any case, this one is about this CD-41 fast battery charger from Yaesu, and this repair video is going to be a little bit different from the others because as opposed to the other ones, I don't have any good documentation on this device. I don't have any schematic, no theory of operation, no parts list, nothing pretty much. So this means that there is going to be more guesswork involved, maybe a little bit more intuition, and I will have to rely on sort of my repertoire of circuits I know in order to get anywhere. But as usual, I will try to make it such that you will see my thinking steps and the thought progress I have in order to hopefully successfully repair this one. Also, I expect this one to be slightly worse build quality than the other two devices that I repaired. So how does it fail? Basically, if you power the thing with 12 volts, there we go, and you take, this is supposed to charge this FT1D, but it also does charge a few other batteries and handheld radios, and I plug it into the cradle. It doesn't charge, right? If I take another battery, this is important in order to rule out that the battery by itself is faulty, but also another battery, both are flat, does not charge. So clearly it's indicating that the battery is full, but that is not the case. I also do know that if the device were operating properly, the full LED, the green LED, should not be lit as long as I'm not plugging in an empty battery in. Then the red one will get, the red one says charging, will get on, and once it charged, the green one will get lit. But with nothing plugged in, the green LED should not be on. So that's basically how the thing fails. A wrong indication here, as well as no charging action. Now, the interesting thing here is I checked the web for anybody to have a similar problem with this thing, obviously. I couldn't find anyone explaining what was wrong and outlining steps for repair. But if I check, for example, this eham.net website that has reviews, there is one guy here that says, well, you're using it wrong. But everybody else is like, the green LED, which is supposed to indicate full charge, is now constantly on. The issue is the green full light stays on and it won't enter the charge cycle. The green LED is on all the time, but it's not entering the charging cycle. And then this guy here, he also has the fault with the green LED permanently on. So clearly there is a systematic problem here. That's also why it got only 1.8 out of 5 points here. And by the way, apparently you can get this for 40 bucks, but even locally I managed to find it for less. Maybe that's the reason why it just doesn't make it for a very long time. In any case, let me open this up, have a look inside and see what we get. Right, so I opened it up and at a first glance it doesn't look too bad. This is the connector to which you apply the 12 volts. There is a fuse, a power resistor here, 2 electrolytics, a discrete diode, some more diodes and capacitors up there, and a power transistor that is labeled with A2183. So I guess this is a 2SA2183 PNP transistor. We'll maybe look at that. Also, you can see the 3 kind of lugs, and if you turn it around, and let me actually get a piece of paper here because I don't want to get the solder paste residue all over. You can see how the 3 lugs will connect to the battery here. So basically that's how it works. Now you can see some more LED stuff going on. That's the two LEDs that are misbehaving. And if you look closely, I'm not sure whether you can see this on camera here, but the work here is actually fairly poor. It's very horrible. I'll include a bit of close-up here for you to see this better, but there is a lot of residue on this board. Also there is conformal coating, but they didn't clean the board properly before applying the conformal coating, so it really looks fairly ugly, and that is a bit of a disappointment. Anyway, there is quite a few SMD transistors on this board. They have labels mostly BR32, BR28, HI5, and I couldn't figure out what those are, so that will add a little bit of trickiness to the job. Now, how do these work? If you look closely, you see that one of these lugs is connected to ground. That's that guy here connecting to ground, which is also the ground of the 12-volt plug here. So one is ground, and one connects to this power transistor that you could see on the other side of the board, and then goes through that series resistor, and there is probably a bit of a control loop going on here. Now, generally, these chargers are not very, let's say, smart, because inside the battery you'll usually find another controller, a battery charge manager, and there is no standardized ways of what is done where, in the external charger and inside the battery pack. But generally, looking at this, I wouldn't assume lots of trickiness going on in here. Most of the circuit here is probably protection and, getting the logics right for these two LEDs. Anyway, so basically the way this works is you take the 12 volts here, and they go through this power resistor here, through the power transistor, and end up here. Now the third lug here, I'm not sure what this is for. Also, this isn't really standardized, but mostly this is either some series resistor inside the battery pack or a thermistor or something like that. So basically this guy generally very often just gives some feedback about the battery status to this circuit here, but we'll see where this leads us. So I will do two things now. The first one is I want to check whether this power transistor is working properly, because this being a high power part, quote unquote, there might have been some heat issues there. So I will check. I will first reverse engineer a little bit of the circuitry and then check this transistor, and if this is a dead end, I look at the LEDs, because we know that the LEDs are not behaving the way they should. So my guess is that we'll be able to track down the problem starting from there. But let's just for fun and maybe also to rule that out, check the transistor first. Okay, so I reverse engineered the relevant part of the circuit here. It's fairly straightforward. You apply 12 volts, it goes through a fuse, through a 4.7 ohms resistor, then through that transistor, which I'm really assuming to be this 2SA2183. The pinout checks out, it makes sense. Then through a series diode to this lug here. So basically, I'm assuming that the base here is going to be controlled such that you'll end up with some voltage at S1 here. That's probably all this charger does, apart from the LED stuff. Now, in order to check whether this transistor is faulty, I'll go and measure the voltages with respect to ground at each of the three terminals. So I will start with the emitter here, which is this guy here, and the emitter is at 12.07 volts. So I'll just write that down, 12.07 volts. Then this is the base here. The base is at 11.89 volts. And at this moment, I really don't care what is hooked up to the base. I just want to make sure that the transistor is working as it should, because this being a PNP transistor, obviously I shouldn't have the 12 volts here at the collector. Instead, well, probably it gets pulled to ground or something. So let's check that. The collector is this guy here, and indeed this is not indicating anything here. So that looks correct so far. So since there is no fault with this transistor, apparently, at least I haven't found one so far, I think I'll dig into the LED stuff here. The device is unplugged right now, and as soon as I plug it in, this LED here will come up slowly. See? It's still increasing in brightness, and now it's kind of hitting that final brightness. So it looks like something is being charged, some capacitor is being charged through a resistor, which then slowly allows this LED to come on. And the goal would be to track down what exactly is going on in this part of the circuit here, and hopefully to then go from there. Right, so what I have so far is the 12 volt coming in from here, go through the fuse, and then end up here, which is one terminal of that resistor that we had above here. And from here it gets to that R5 resistor here, which is 1.8K, and then makes it into the green LED that is lit, so the circuit is powered right now. And then on the cathode of that LED, there is this 3-terminal device, which is probably a transistor, and I'm trying to figure out what exactly it is and what its pinout is. So I think it's a safe bet that it is a transistor of some sort. This being on the low side of things, probably it's either an N-channel MOSFET or an NPN transistor, BJT. Now, you probably saw that in the time lapse. I tried to measure the PN junctions of this transistor, but I failed to do so, which is hardly a surprise, because due to all the other parts that are here in circuit, it would be more of a lucky shot to actually be able to measure that. So what I will do instead is I will measure the voltages on each of the 3 pins of that 3-terminal device here. Now, the first one is the cathode of the LED. Now, if this is an NPN transistor, I expect this to be the collector. But anyway, I've got 0.837 volts here, and on the other side of that SOT23 package, there is 2 more pins. One is at 0.682 volts, so that's lower, so that could be the emitter. And the third one is 1.362 volts, so that's almost 2 PN junctions from ground. And in fact, if I count the base emitter junction in here as 0.7 volts, as well as this diode here that goes down to ground as 0.7 volts as well, I end up with 1.4 volts. So my guess is that this guy here is the emitter, and this guy is the base. That also means that I should have about 1 PN junction between this guy and this guy, which is the case. So that means that this is in fact the collector. Oh, right. So that would be the collector here, the emitter, and that then goes into a diode down to ground, and that's the base. we have to see what is kind of upstream of that base and why there is current. I expect one of these two capacitors here to get charged slowly as the LED goes on. So I'll try to reverse engineer this a little more and see what we get. Okay, so I've found something interesting here. I started from the back this time, so this transistor, the Q4, is the transistor that we talked about before. It's the transistor that is getting turned on as you plug in the power cord. And before I didn't draw out anything hooked up to that base here, but now I did. So basically that's what is connected to the base of that transistor. And working from the back, first there is a 56K base resistor, and then probably what is a bleeder for this capacitor of 6.8K, and then a 470 microfarad electrolytic capacitor, and a series 39K resistor. So I'm assuming that there is some voltage here at that node, and resulting from that some current flowing through that 39K resistor, charging the capacitor, at some point turning on this transistor, because this is an RC circuit here. So basically you apply some voltage here, capacitor gets charged, and once it's sufficiently charged, there is enough of a base current to turn on the transistor, and as a consequence of that the green LED will go on. So now the question becomes, why is there this base current? Because remember, in the end, as long as we don't hook up any battery, the proper behavior of this circuitry here is not to light the green LED. So it boils down to why is there a voltage here? There shouldn't really be any voltage, because any voltage here will charge that capacitor and as a consequence turn on the transistor. And I see two reasons for that, because there is kind of two tracks getting off that node. One, so that's the simpler one. This goes to the base of the power transistor that we discussed at the very beginning. And remember, we had like 18, actually 12. We had like 12 volts here at the base. And these 12 volts here, they get tapped off with a diode and end up as a voltage here at that node. So it is possible that at this point, the base here should not be on. I don't think it's the case, but anyway, this is a possibility that we shouldn't have any voltage here, and then if we have no voltage here, we probably don't have any voltage here either. The other possibility for this, because this looks like there is some transistor circuitry here that shuns that basically pulls this node to ground, and this is why I believe that we should have voltage here and this circuitry here on, shunting any current to ground instead of it going in here. Because if we do have 12 volts here and nothing connected to that node, like the transistor circuit here is off, we get exactly the behavior that we observe. So I believe that for some reason, whatever is here is misbehaving. So I might be wrong on that, by the way. But in any case, I'll check what we have here and then proceed from there. Okay, so I just had a good look at what is connected to that node here, and I just wanted to continue to sketch it out, but I think just by looking at these two transistors and the way they are connected, I'm fairly confident that this is a Darlington configuration of those two guys. That would make sense because this has to shun a lot of current potentially. So as you can see, the assumptions here are really stacking up, but I'll just draw it because from the top of my head, I don't see anything else, any other circuit that would make sense here. So I'll just draw the first transistor here with the base that is used for control, and then there will be a second transistor. This emitter here goes into the base, the collector is sheared, and you can see that there is like these two guys are sheared here, so it sort of all makes sense so far. And then one emitter should be grounded. Let's see if we can get that. Yeah, it's hard to see, but this guy here goes into this ground plane there, so that all makes sense. This is grounded, and we have to see what is going on with that base here. So basically probably I should redraw this transistor. So I'm going to redraw this transistor to get a bit more space here, and we are wondering about how this base is controlled. Okay, I'm sorry, but I have to reshoot that one because I just found something that was fairly weird. If you look at the base here, this is the base we were talking about before, so it's sort of the way to control the Darlington configuration of these two transistors here. If you look at this base, there is a pull down, so that doesn't really matter that much. And if you follow that trace here, you first get to that capacitor here, and you follow the trace further, you see that it splits here. It splits into one trace that goes down here and one trace that continues kind of horizontally. Now, following the trace that goes down, you end up here. But this is still the base, so instead of kind of turning right here and doing the whole loop, they could just as well have turned left and connected it straight to the base. So that's probably just a mistake here. But in any case, this then goes under the two transistors. You can't see that, but I buzzed it out to that solder joint here. So that's a bit complex right now, because this base here is controlled by no less than 3, let's say, sub-circuits. One is the one that you reach when you continue horizontally here, that has to do with the feedback loop. The second one is the one down here because there is a trace here going there. And the third one is this solder joint is just a solder bridge here, or rather a jumper wire going up there, and then this has to do with the feedback pin of the battery pack. So 3 things are controlling the base here, apparently. One is the feedback of the battery, one is the feedback of the whole controller here, and the third one is this thing down here. And I have to pick which one I want to follow first. Now, I don't want to deal with the feedback over here as long as I can avoid it. And I think I'll look at that first. I don't think there is any logic here, but I wanna rule that out because I'm not exactly sure what's going on there. So I'll look at that first. This looks reasonably simple, and then I'll follow the route with the jumper and the feedback lug here. So let me reverse engineer that bit here and see where we get. Right, so this might look a little bit strange at first glance. This here is the transistor that is part of the Darlington transistor array. So basically, this is the base that I talked about before that is controlled by the 3 subcircuits. And one of these subcircuits is what's going on here to the side, and that's what I drew here. So basically, there is a 1K series base resistor, a 680 ohms pull down, then 2 diodes back to back. And I believe that this is a Zener diode, although I wasn't able to measure the Zener voltage, but anything else wouldn't make sense at all, in my opinion. As well as a 220 ohm series resistor and the fuse that we had before. So basically, I believe that this is some overvoltage protection circuit. As the voltage here gets much higher than 12 volts, you will have some Zener drop here, some Zener drop across this diode, the normal PN junction drop across that diode, and the voltage at that node will start to increase. if the voltage here is sufficiently low, that's not going to happen, and basically the base will be grounded and this transistor will not be active. So I believe that's what it is, and to make sure that this is working properly, basically this should be off, right? So I'm going to measure the voltage here, 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 and here along this path and see what we get. I'll start with the connector, and obviously at the connector we should have 12 volts. That's fine. The other end of the fuse, still 12 volts. That's also one end of R17s there. So I'm going to directly measure that node here, which is still 12 volts. And now we should run into the Zener drop here. Okay, now that is interesting. If you know what's going on there, put it in the comments. But so all of a sudden we get a negative voltage anyway. So that would be here, and that node here should be at ground. And that is the case indeed, as by this pull down resistor here. So in fact, this transistor here is off, and that's exactly what it should do if the theory is right that this is a overvoltage protection circuit. So unfortunately that was the wrong sub-circuit, and next I will look at this feedback pin here and what's going on here, because that also feeds into this transistor array. Okay, so to be honest, I'm really not sure whether I got that one right. But first things first, let's recap what we have. We figured out that the Darlington array formed by these two transistors can shunt current flowing through that resistor here down to ground. Now, this is happening when these transistors are on. When they are on, then the current through that resistor gets shunted to ground. If this array is off, however, the current flows through that resistor here, charges that capacitor, and as a consequence, after some time, this transistor here turns on and the green LED gets lit, which should not happen under these conditions. So let's check what's going on with that transistor array. I should have done that earlier, but basically the base here sits at 0.36 volts, and that is not enough to turn on this array. So the theory here would be that this array should be on. It isn't, and we have looked at one sub-circuit that is tied to this base here, which turned out to be the overvoltage protection circuit, and that works as it should. So I don't think there is a problem here. So further things tying into that base are what presumably is the feedback control loop of this crude regulator here, or whatever is going on here, and that's what I try to reverse engineer next. So if we look, that's the same transistor with a base of the Darlington circuit, and there is a jumper wire here jumping from here to there, and then this diode here, D9. And then it gets kind of tricky. But another thing that ties into this circuit is from the 12 volts, there is the fuse again, it's always the same fuse, right? Then R1, a series resistor, and again a reverse biased diode. And as before, I think this is a Zener. So if I go and measure that, then I get obviously the 12 volts from the supply, and on the other side of the fuse I still have 12 volts. And then if I measure that node here, I get 6.1 volts. So this appears to be a 6.1 volt Zener. Now, if I measure the cathode of that diode here, the Zener diode would be that diode down here, that guy here. So again, well, that's ground obviously, and the cathode is 6.1 volts. So is the anode of the series diode D1. And if I measure the cathode of that guy, I get a little less because there might be a bit of a voltage drop. You know, this is also jumping up and down because because I don't have proper connection here, but anyway, so this appears to be a normal quote-unquote series diode. Anyway, that would be then that node here, and then there is again a weird 3-terminal device, and I'm not really sure what it is. One thing that is a bit unusual is there is a 6.8 meg resistor involved in this circuit, which is one of the reasons why I believe that this is a MOSFET. Because we've got like high impedance resistors, you know, it doesn't have to be, but that would be one indication, although there is something really strange with that resistor, because the way it's connected here hardly makes any sense. But anyway, and another reason would be this here actually goes to that lug, to that lug here. This got disconnected here, unfortunately. Which is the feedback from the battery, whatever it is. So this means that they connected the gate directly to something the user can touch. And if that's really what they did, it would explain why this part is faulty. So assuming this really is a MOSFET, I have to figure out whether it's an N-channel or a P-channel MOSFET. And the theory here is that probably the voltage here, the 6 volts at the zener, somehow gets switched through to the Darlington transistor circuitry that we saw before. And this circuit here would actually do that. You know, if you pull the gate low, then the P-channel MOSFET turns on, and this is exactly what's happening. And if you tie it high, this is not happening, which is also the reason why I think this is a P-channel MOSFET, because if it were an N-channel MOSFET, to turn it on, I would have to pull it above the 6 volts here, and I don't think the battery can do that through the feedback pin. So I think I'll go with a theory that this is a P-channel MOSFET here, although to be honest, you know, this 6.8 meg resistor looks like an attempt to protect the gate, maybe, or to pull it to some known potential if nothing is connected to that second lug here, but that's not the way you do it in either case. Okay, so after some more thinking, I really believe that this is a P-channel MOSFET. One reason for that is that 6.8 meg resistor. Now, if this were a PNP, which could basically accomplish the same thing, there would be even less reason for that 6.8 meg resistor here. Another reason is that if they really tie the gate to that lug that the user can touch, there is no wonder that this breaks down. As we could see, this is, as I showed in the very beginning, many people are having this problem. So, and also, if this was a PNP, then I would be able to measure the base emitter junctions, which I can't. However, there is something really interesting. First of all, if I put the multimeter into diode mode, I can measure what appears to be the parasitic diode of the transistor. And second, if I put it into ohms and I measure the resistance between the source and the gate, I get 4.3 kilo ohms, and that should not be the case. So this really looks like this MOSFET here got zapped by ESD discharge, and the isolating oxide isolating the gate from the other two terminals broke. So I think what I'll try to do is remove the transistor from this PCB, try to figure out whether it behaves like any transistor should behave, no matter what it is, and if it looks more like a MOSFET, I'll replace it with a P-channel MOSFET and hope for the best. Right, so I successfully removed that part and tested it, and it very much behaved like a dead MOSFET and not so much like a dead bipolar transistor. So I decided to take the risk, and I replaced it with a P-channel MOSFET with this one, actually, that I got for some random project in 2012. And of course, because I cannot figure out what transistor they put in, this is a bit of a long shot. Although if the circuitry works pretty much the way I think it does, this should in theory work. So bear with me. I haven't tried this before, I promise. So I'll go and grab the 12 volts, plug this in. Now, in contrast to before, the green LED should not go on. Okay, and that seems to be fine, so that is already a minor success there. So either this is working the way it should, or it's not working at all anymore. And now I'm going to take an empty battery and just hold it to the connectors, and now the red one should go on. And that is the case indeed, and there is no smoke. So what I will do is I will take a few more measurements to make sure things are working the way they should, then put it back together and see whether it manages to charge a battery. Right, so to summarize, this is a battery that is almost full, and towards the end of the charge cycle, I forgot about that, the red one actually starts to blink. So if things work out the way they should, this should switch to green fairly soon, because this is pretty much full. So a couple of points. First of all, I'm sort of disappointed by Yaesu that they managed to design their product in such a crappy way. It just turned to green, by the way. So if I unplug this, the green goes off. So yeah, it looks like it's really working fine. How cool is that? Still very disappointing that they exposed the MOSFET gate through that center lug here. So do not touch this guy here, because that will sooner or later break the MOSFET. Now obviously, to properly fix this, some protective circuitry has to be added, and I'll discuss with my friend, because this is not even my own charger. I'll discuss with my friend what to do. This probably involves cutting traces, and I don't want to do that with his unit. I already broke it once, so that's enough. And lastly, if you have one of these chargers that is newer than that one, because that one I think was acquired in 2012 or 2013, if you've got one that is newer, I would very much be interested in whether Yaesu fixed this issue or not, because based on this user feedback here that I showed you at the very beginning, Yaesu is aware that there is a problem with that charger, and it would be interesting to see whether they actually got around and fixed that, or whether they're still shipping units that are doomed to failure. So anyway, thank you very much for watching. That was a bit of a messy one, but in the end things really seem to work, so I'm very happy. And well, yeah, thank you for watching. If you have comments, please post them down below, and see you next time.